All right, welcome to your canonical correlation lesson. This guy is getting ready to run a correlation. You can tell by how focused he is on that canon. Maybe not. Anyway, correlation, canonical correlation, that is just a multivariate correlation, meaning that you have multiple variables on one side, on the x side, and multiple variables on the y side. So the reason for the term canonical is not because of canons in the military sense. It is more a canon that is a standard of principle or a single criteria. And so that's where this particular method gets its name from, because you're reducing multiple variables into one kind of on one side of the correlation, and then reducing another set of variables on the other side of the correlation, and reducing them in the sense that you're describing the correlation between one side, one set, and the other side. So this might remind you of correlation, first of all. It also remind you of factor analysis. And so somewhere in between is where canonical correlation lies in its utility. If your goal is more to define your variables or define, let's say, a factor or set of factors, by way of many variables, and your goal is more along the lines of measurement or precision of measurement or trying to capture a psychological construct, that all lends itself toward factor analysis, of course. Whereas correlation is just between describing a relationship between two variables. A canonical correlation is describing a relationship between two sets of variables, and the measurement of the sets, how many variables go into each set, is not necessarily the primary focus, as would be in factor analysis. The primary focus is more like reducing those sets of variables into entities that can then be correlated with each other, and so the focus is more on the correlation that comes out of it. So you can be the judge as you go along as to the utility of canonical correlations, and where they might fit in between factor analyses and correlations, let's say. So, like I mentioned, there's two sides, two sets of variables here that then are correlated with each other. I'll give you a little bit of the math. We have a little bit of matrix algebra to get through in order to describe the underlying principles, the underlying algebra of what a canonical correlation is. We won't go into great depth necessarily, or any larger examples than just, let's say, two variables on one side and two variables on the other. But of course, there are resources available for you if you'd like to look into this further, if you end up running it for your thesis, for example. So the math behind it is matrix-based. It is, to understand it, is to go back to multiple regression, actually, and understand the matrix approach to multiple regression, which we never covered. So I'm going to bring back our multiple regression example from an earlier lesson, earlier video, with mothers and fathers' anxiety, predicting baby's birth weight. We have the regression equation here. This is your unstandardized regression equation. Here's your standardized regression equation with the betas in there instead of the b's. And so the standardized values were negative 0.81 for mother's anxiety, suggesting a strong relationship, a negative relationship, although I think with such a small sample it came out to be non-significant, but certainly a stronger relationship than the one for father's anxiety, negative 0.09 here for 6 families. But that's your standardized regression equation. And so we take those numbers, or we store those numbers as our answer, and then we try to get them by way of matrix algebra. So the conversion here is from correlations to betas, ultimately. So we're taking our correlations between x1 and x2, x1 and y, and x2 and y, again based on our small sample example here. And we're going to organize them in a certain way in matrices, like so. This is a correlation matrix including y. So for example, x1, x2 here is negative 0.199, x1y is negative 0.791, and we're including the ones in the diagonal, and the above and below the diagonal are the same as each other. So then we can break this correlation matrix up into sections. Now for multiple regression, this is not super useful because we have our beta formula that does not require matrix algebra, but in canonical correlation, we're going to see an extension of this example that does require matrix algebra. So that's why I'm giving you the original example here. And to break this up is central to what is going to be useful to get the ultimately the betas here for our regression, and then the appropriate numbers ultimately after that for the canonical correlation. So we have a matrix of correlations between IVs, and then a matrix of correlations between the IVs and the DV. In this case, there's only one DV. So this is what they look like. These are just sections of that correlation matrix. So if you have your notes next to you, maybe you can refer back to that overall correlation matrix, and you see how the sections break down. I'll give you one flip here. If you're looking for the 1, negative 0.199, negative 0.199, and 1 matrix, if you go back here and flip back here, that's the top left, right? That's the matrix of IVs with each other. And so you do include the ones there. The matrix of correlations between IVs and DVs, negative 0.791. That's only one DV, so you only have one column in your correlation matrix here in section 2. And so then we arrange them like so to get betas. This is kind of, we could go back to our non-matrix version of the beta formula, look at that, then go and look at this and compare and try to understand a little bit. That would be week 2 of correlation. This is only week 1 of canonical correlation. Week 2 would be to break this down a little bit further and try to figure out why these numbers in this arrangement give you your betas. But meanwhile, this is your formula. You've got that first matrix, which was your correlations of your IVs with each other, and you are putting that to the negative 1, which is the inverse of that matrix, multiplying that then by the next one, which was the IV DV correlation matrix, and that ultimately is going to get you your betas. So just a reminder here, we did cover this when we did profile analysis. 2 by 2 matrix inverse looks like so. So if you're taking the inverse of a matrix, here's what it looks like. And so we apply that here. And so I'll let you guys, I mean, I don't know, you've seen this stuff now if you've done the profile analysis. So maybe you're starting to get to the point where you're like, aha, I know how to do this. This is fun. Okay, maybe not fun, but this is doable. How about that? Is that better? All right. So, so this is your matrix inverse laid out. And so if you're doing this on your own for the new example in the homework, let's say, you could compare this process to that one. So you take that inverse and then you multiply here, and you ultimately get the 0.81 negative and the 0.09 negative, which match our betas that we already got from our multiple regression. So that was unnecessary. I did not run you through it before when we did multiple regression because it was unnecessary. But this leads us, this splitting up of this correlation matrix leads us to the canonical correlation process. And so here we go with that. So a reminder here, the canonical correlation is going to be, in this case, between two sets of two variables. Again, we could have more than two per set. But let's look at the theory here. So the theory is no longer, see, again, with every new method, you have to kind of think about what would a hypothesis look like? How does this fit into your possible future studies? How would you apply the scientific method? So in this case, with the regression, we had mother's and father's anxiety predicting baby's birth weight. That was like a cause and effect implication in that higher mother's anxiety, higher father's anxiety might lead to a baby weighing less or being slightly less healthy. So now we're backing up and we're doing a correlation here. And so we're not assuming or not predicting any cause. We're not implying any cause with our hypothesis. We're just saying now that mother's anxiety and father's anxiety on one side or in one set are collectively correlated with this other side, which now is baby's birth weight, and we're adding in a second baby measure, which is baby's anxiety level, and a scale of 1 to 10. Presumably, the babies are self-reporting their anxiety. I suppose that would be unrealistic, although I feel like we could probably do this in real research by asking the parents how anxious the baby is. I don't know, something like that. Or we could do it observationally. percentage of time that the baby spends crying. I don't know, something like that. Uh, in the end, we have extreme anxiety occurring for all 6 babies here. That's pretty funny. Okay, anyway, moving on. Our new correlation matrix adds in that Y2, which is your baby's anxiety measure. Um, and we're going to go forward from there. We need to split this thing up. So now we don't have, I mean, it's a little bit expanded. It's got 2 IVs now. We've got 2 DVs as well. Before we had 2 IVs and 2 DVs. And it's interesting to call these baby measures DVs because, well, it's a correlation. So we're not actually saying that they're dependent on the IVs necessarily in our hypothesis. We're just labeling them as Y, or a dependent variable, typically is labeled as Y, for the purposes of splitting this matrix up into sections. So sometimes in a canonical correlation study, you might have one set correlated with another set, and you just have to kind of arbitrarily choose one as the IV set and one as the DV set, I think. That's been my experience when I've seen these studies. So anyway, we have correlations between IVs. We also have correlations between DVs. Now, before we didn't have that because we just had one DV. And then the 3 and 4 are just sort of the transpose of each other. So we have IVs with DVs, and then we have DVs with IVs, which is 3 and 4 are the same. They're just going to be arranged differently in rows and columns. So the number 1 matrix here, correlation between IVs, that's the same as it was before because our IVs are still the same. Correlation between DVs, however, we now have this negative 0.104 between Y1 and Y2 that we didn't have before. Correlations between IVs and DVs are here, and then like I said, you just turn it on its side for the correlation between DVs and IVs. So if we were to go back a few slides to this particular correlation matrix as a whole, you begin to see the pattern. You see that the 1 and negative 0.199 on the top left, that's your correlations between IVs. So your top left quadrant is that. The correlation between DVs is in the bottom right, negative 1.104 and the 1 there. And then the other 2, you just take bottom left and top right. So for 3 and 4 here. So again, it's just sectioning off that matrix into these 2 by 2 matrices here. And then we plug them in, and we just got to be careful we plug them in the right place. So the magic matrix, I don't know how magical this really is, but this is the canonical correlation fundamental matrix, because ultimately it's going to give us what we need to describe that canonical correlation. So we go in order here. The 1, negative 0.104, that's the correlations between DVs, and that's the first matrix, and you inverse it. Then you go 0.791 negative, 0.069, which one was that? That was number 3, correlations between IVs and DVs. So it's number 2 comes first, correlations between DVs. Then number 3, correlations between IVs and DVs. And you can't forget to inverse that first one. Then you do the correlations between IVs, third, and inverse that. And then by process of elimination, the other one there, that last one, is it's number 4, which is correlations between IVs and DVs. Okay, so we go through this step by step. Again, hopefully you guys are really into the matrix algebra now. You're really looking forward to multiplying all these. Okay, maybe. Okay, so here's the reminder. Inverse of a 2 by 2 matrix. You can file this away and use it when you're doing this on your homework. So I didn't demonstrate this in great depth here, but I did a little bit better earlier in the video. Again, you can practice this on your own. So you take those inverses. I did them first before multiplying. You can do the first one first and wait on the second one if you want. But either way, you take those inverses, then you have this train of multiplication here. So I'm just going to, I have the recommended method here in one slide for multiplying 2 by 2 matrices by each other. So you can take this and see if it looks like it makes sense, then that's good moving forward. So the first matrix, once you inverse it here, becomes 1.01 on the diagonal and 0.105 on the other diagonal, top right and lower left. So you take that and you multiply like so. So for example, the top left of the resulting matrix you have the top row of the first matrix, 1.01, 0.105, multiplied by the left column of the second matrix, 0.791 negative and 0.546, and you distribute it out. So it's like top left multiplied by top left plus top right multiplied by bottom left, right? If you're following along with the numbers, hopefully you are, or if you're not, you might be able to see the patterns just by staring at it for a minute or two. So my rule of thumb on this is just when you're going for the top left, you take the top of the left matrix, top row, and the left of the right matrix, the left column there. If you're going for the top right, you go top of the first matrix, right of the second matrix, right column that is, and so on, so on. All right, so this is your 2 by 2 matrix multiplication. You do the first one, then you have another one, and then you have another one. So it'll be 3 2 by 2 matrix multiplications. You can use Excel, hopefully, to your advantage in this process. In this case, you're going to end up with a magic R matrix of the matrix that you see there in the bottom of this slide. Okay, so what does this mean? Why did we do that? Well, there is a little bit of mystery again in this process. Eigenvalues creep in again. We use eigenvalues a lot in factor analysis. The eigenvalues tend to be these values that describe a matrix and how many dimensions or factors there are for factor analysis. Here it's going to allow us to figure out how many canonical correlations we have, how many ways there are to describe the relationship between set 1 and set 2. So instead of deriving factors by eigenvalues, now we're deriving the number of canonical correlations, the number of ways that set 1 and set 2 may be related, because there may be multiple ways. There might be and we'll see how this interprets here, but there might be one main reason that set 2 and set 1 and set 2 are related, and then one or two even smaller reasons. So what is a canonical correlation? Canonical correlation is equal to the square root of the eigenvalue of that matrix that we just got. So what is an eigenvalue? Well, here you go again with the eigenvalue explanation from Tabachnik and Fidel. Not particularly enlightening, but like I said, it is a value that sort of creeps in as a descriptive value of or set of values of a particular matrix. So in this case, again, we're deriving canonical correlations via eigenvalues. And the word interpretation is more like for each canonical correlation, again, it's a square root of an eigenvalue now. So for canonical correlation, if you square it again, so I guess a canonical correlation squared is now an eigenvalue. And if you do that, it represents the percent of variance in one variable accounted for by another variable. So this is our R squared for canonical correlation as represented by an eigenvalue. These eigenvalues are amazing. Okay, like I said, there might be more than one that comes out of a solution. So there might be more than one way of describing set 1 and its relationship with set 2. For our example, we do end up with 2. Okay, so here's your canonical correlation diagram laying out all of your relationships here. I'm going to take you through it real quick, and then we're going to see where these numbers came from in SPSS. So first of all, we have 2 proposed relationships, and we're going to see how SPSS gives us 2 eigenvalues, which is why we were forced to represent our set 1, set 2 relationship twice. So the first one, 0.96, a high correlation or a strong relationship between set 1 and set 2. And so we look back at so we could also name our set 1 and set 2. So I'm going to say like parents' anxiety for set 1, and let's say baby's health for set 2. We could do that. So we look back, and then for the first, the upper part of the diagram there, the first parent's anxiety variable is composed mostly of mom's anxiety at negative 0.96. Dad's anxiety is not as strong there, negative 0.1, and that those are negative values. So the higher the mom's anxiety, the lower the overall set 1 value. So what that tells us is like set 1 is like a lack of anxiety, I guess you could say. Parents' lack of anxiety is correlating highly with a high value on set 2, baby's health. So a lack of anxiety then represents a stronger or a higher value on baby's health. Baby's health is represented by a high birth weight or a positive value 0.82 and a low anxiety or negative value 0.66. So the conclusion there would be something like as parents' anxiety goes up, when parents' anxiety is primarily represented by mom, as that goes up, the baby's health goes down, or as the mom's anxiety goes down, the baby's health goes up. So that was the first one. The second one is a weaker correlation, 0.25. And that one is when you look at parents' anxiety, it's primarily represented by dad, 0.995. Mom's is actually negative there. So parents' anxiety is, again, primarily represented by dad, with mom's anxiety actually taking away from it a little bit. Baby's health then is represented by a higher birth weight and a higher anxiety. Those are positive values on the right side there. So what that tells us is as dad's anxiety goes up, the baby's birth weight goes up, which is a good thing, but the baby's anxiety also goes up, which is a bad thing. So dad's anxiety has sort of a differential, maybe non-quite conclusive effect on baby's health, and especially not conclusive because that 0.25 is rather low compared to mom's effect there, or the one that represents primarily mom's effect, which is the upper relationship there. So let's look at SPSS and figure out where these values all came from. So first of all, I recommend entering your data as x1, x2, y1, y2, like so. So if you take the variable names out of there, it actually helps you out because you're going to be running this syntax. Yes, we're doing syntax, but it's a fairly sort of standard short script here. It should be relatively easy to run. It actually runs through Manova. Not exactly sure why that is, but canonical correlation is not one of the default options in SPSS. So we have to kind of get it through some sort of back channel way of grabbing it here. But you see the y1, y2 with x1, x2. If you didn't have your variables labeled like so, you would need to then change the script as well. So that's why I recommended just keeping it simple and calling them y1, y2, x1, x2. Again, in this case, x1, x2 is parents' anxiety, and y1, y2 is baby's health. So we're going to highlight this, and we're going to click the play button, and you're going to see your output. Now I'm going to try to make the font bigger so you can actually see this. Okay, so this is your output. Looks a little bit different because we ran the syntax in terms of the font and the layout of it, but I'll show you where it's like a scavenger hunt here to find your different canonical correlation variable values that you need. So the first section here that you need is the eigenvalues and canonical correlation section. So here you find the 0.95778 and the 0.25236. If we go back to the diagram, that's the 0.96 and the 0.25 that we fill in here. Again, it lists 2. Sometimes it might only list 1 in this case, so then you would just go with one canonical variable combination, canonical correlation. But here we have 2. So we pull those 2 values out, and then we scroll down to the correlations between dependent variables and canonical variables. So this is going to be right here. Let me put that at the top. Correlations between dependent and canonical variables. 0.8176 and negative 0.65754. Those are your birth weight and baby's anxiety relationships here with set 2. And then, oops, I scrolled away from it. Let me get it back. Okay, there it is. So it organizes it by dependent variable and canonical correlation 1, dependent variable and canonical correlation 2, which is 0.58 and 0.75. So those 2 values go in here. So it separates those out from your independent variables. So then you need to go find the correlations. You would think it would be labeled independent variables, but instead it is labeled as a covariate. So I'm going to scroll down a little bit farther. I scrolled too far. I was looking for independent variables, but it's correlations between covariates and canonical variables here. And so you've got your 0.956 negative and your 0.097 negative, which became these two guys, 0.96 and 0.10 negative. Again, these are now independent variables, and the relationship for the first canonical correlation there, or the independent variables relationship with their particular set. In this case, it's parents' anxiety. And then we go here, we have negative 0.29 and 0.995, and those are your mom's anxiety and dad's anxiety relationships for the second canonical relationship. Okay, that's it. That was there's lots of other output here to be had, and a little bit more depth of understanding that may come from a more in-depth study of canonical correlation. In the end, we have a strong relationship to represent our parents' anxiety and baby's birth weight, set 1, set 2, and then a weaker one that we could, like if we were to write this up, we'd be like, well, mother's anxiety seems to have when parents' anxiety is primarily measured by way of the mom, that seems to have a pretty strong impact on the baby's health, and that is that the more anxiety the mom might experience, the worse the baby's health, or the less anxiety the mom experiences, the better the baby's health. But we can also say that the other way, the baby's health then might cause the mom anxiety or not, depending on what it is. So we can conclude pretty strongly with a 0.96 there, but again, we don't have significance values for these particular relationships. So with only six families in our data set, there is some limit to how much we really should conclude here. And again, there's more nuance to what we might want to write up if this were a write-up of canonical correlation. That second variable, 0.25, that second canonical correlation, 0.25, weaker, but still worth mentioning, certainly. And so, yeah, if you want more information about how to write up a canonical correlation, someday you might do one. Maybe you're watching this 25 years later and you're writing up a paper. Okay, that seems unlikely. I probably will have deleted the video by then. But anyway, if you would like more advice, we can sit down with it, where you can look into some empirical articles that have used this stuff and see how these diagrams fit in and how the significance values may need to be reported as well. But meanwhile, that's your introduction to canonical correlation.